Hello and welcome to Podcast.init, the podcast about Python and the people who make it great. When you're ready to launch your next app or want to try a project you hear about on the show, you'll need somewhere to deploy it, so take a look at our friends over at Linode. With the launch of their managed Kubernetes platform, it's easy to get started with the next generation of deployment and scaling, powered by the battle-tested Linode platform, including simple pricing, node balancers, 40 gigabit networking, dedicated CPU and GPU instances, and worldwide data centers. Go to pythonpodcast.com/Linode, that's Linode, today and get a $100 credit to try out a Kubernetes cluster of your own. And don't forget to thank them for their continued support of this show. Your host, as usual, is Tobias Macey, and today I'm interviewing Jian Tang about TorchDrug. So, Jian, can you start by introducing yourself?
Thanks very much for the invitation. So glad to be here. My name is Jian Tang. So I'm an assistant professor at the MENA, Quebec AI Institute, which is a research institute focused on machine learning, artificial intelligence, founded by the Turing Award winner Yoshua Bengio. So my main research interests focus on deep learning for graph structured data, or in other words, graph repetition learning, graph neural networks, geometric deep learning, knowledge graphs. And also specifically, I'm very interested in applications like drug discovery or material discovery.
And do you remember how you first got introduced to Python?
So I remember I first got in touch with Python when I was a PhD student. That was back to 2010. So at that time, most of us mainly use programming language as C++ and also Java. But then I knew a lot of people were starting to use in Python. Many of my friends told me Python are very easy to use and the community is really growing. And there's a lot of very useful tools that we can leverage. So that's why I started to get interested in Python and also start to learn Python.
And so one of the particular areas of focus that you have right now is the TorchDrug project, which you mentioned is being used for some drug discovery use cases. And it seems to be a fairly well-polished project. And I'm wondering if you can just give a bit of an overview about what it is that you're building with TorchDrug and some of the story behind how it got started and why you decided to focus your efforts on that particular area.
Right. So maybe I can give a little bit story about my research background. So as I just said, my research focused on deep learning for graph structured data. But in the first place, when I was a PhD student, I was not working on deep learning. I was working on machine learning, but more classical machine learning models, statistical topic models. But then back to 2012 or 2013, that was my last year PhD. So deep learning was starting to get to very hot. And then so basically then I feel I was really interested in getting to deep learning. I want to move to deep learning. But then at that time, deep learning was mainly used to applications like computer vision, speech recognition, and natural language processing. Then I wondered, okay, I want to work on deep learning, but I may not want to work on those applications because I'm not as good as those people. So maybe I can find a new area, a new domain, and I can apply deep learning techniques to those applications. Okay, because for me, I was always interested in graph data. So I was very active in the data mining community. So at that time, in data mining communities, people are really interested in networks or graphs. Because at that time, people were very interested in analyzing Twitter data. Twitter, we have a lot of network, right? So followee is social network data. So I was very interested in graph data, network data. But people in data mining community, they don't know deep learning, right? For people who work on deep learning, they don't know graph. They may work on computer vision, natural language processing, or speech recognition. And that's how or where I found a big opportunity, basically trying to connect the two community and then start to work on deep learning for graph structured data, or we can say graph repetition learning. So that was back to 2012, which is the last year of my PhD. And then after my PhD, I worked in Microsoft Research. I continued to work in this area. I feel there's a huge potential. And then after working for 2 years at Microsoft Research, I want to go back to academia. And that's why I quit my job in Microsoft Research and then did a postdoc in University of Michigan and also Carnegie Mellon University. And then afterwards, I found a faculty position at MENA, where I am now. Okay. And then when I started my faculty position at MENA in Canada, I already worked on graph repetition learning for around that was 2018. I already worked on graph repetition learning for 4 years. And then I was wondering, what would be the future for graph reputation learning. So besides like applying them to data like social network, which is also exciting, but I feel like we could like find something more interesting. Then I start to like think about like what could be the key application for graph reputation learning. I realized that like in biology, in drug discovery, so we have a lot of like graph structure data. We have a lot of graphs like molecules, proteins. They can be represented as graph. And also in biology, we also have many like different network like protein interaction, network interactions between proteins and drugs. And also, when I was in high school, our teacher told us like 21st century is going to be the century of biology. In the bottom of my heart, I was very interested in biology. And of course, later, because I work on AI, of course, we don't believe 21st century will be the century of like biology. We believe 21st century is going to be the century of like AI, right? But then I feel like maybe the best domain I can work on is really in the intersection of AI and biology. And that's why I guess I get very interested in working on AI for drug discovery, right? So my group has been focused on like AI for drug discovery in the past 4 years, basically mainly developing graph machine learning techniques for drug discovery. So TorchDrug is really basically ensemble all our previous efforts in drug discovery in different tasks into a very like a unified system. So it basically covers many fundamental tasks of drug discovery. For example, like a de novo molecule design, that means we want to develop totally a new molecule. So in order to that, there are a few very fundamental tasks. For example, given a compound or molecule, we want to predict its chemical property or biological activity. So that's one very fundamental task. And the second one is like a de novo molecule design and optimization. So basically, we want to search for molecules with design properties. We are bind to a protein target, can be synthesized or has low toxicity, right? And then, so this is a second problem, a very fundamental problem called like de novo molecule design and optimization. And once we are able to identify a design molecule, and then in practice, we also have to care about like, can this molecule be synthesized in practice? And this is related to the problem called like planning or prediction. That means we want to find a set of like molecules or reactants based on which we can synthesize the design, the target molecule, the molecule structure we want, which is searched in the second problem I just described. Okay, so these basically all these very fundamental tasks are related to de novo molecule design. That means design a new molecule structure. And besides like design a new molecule, so another solution for drug discovery is called like drug repurposing. That means, so instead of like trying to design a new molecule, a new drug, so we can repurpose some of the existing approved drugs which are used to treat other diseases, and we can repurpose those drugs to treat a new disease. Because like for COVID-19, like take this example, developing a new drug takes like a really long time. It's almost impossible to quickly develop a new drug. So then a more practical solution would be really trying to repurpose some of the existing drugs. For example, those drugs which were developed for treating SARS, right? Because COVID is very similar to SARS, maybe the drugs which could be used to treat SARS could be used to treat COVID as well. So that's basically the second type of like drug discovery solution, which is basically trying to repurpose some of the existing approved drugs for treating new disease, and which could be much faster, right? So that's basically a quick introduction to drug, and also basically related to like how I got into this journey.
Sounds like some of the primary goals of the project are for some of this molecule design and discovery, and like being able to make the search space tractable in, a reasonable amount of time. If you're trying to do that by hand or by actually synthesizing the molecules and testing them out, it's going to take a lot more time and expense. And so I'm wondering who are sort of the target users of the project, and who are the sort of targets in terms of the outputs of what the project is able to create.
So basically, the goal of creating this platform is really trying to accelerate the progress of AI for drug discovery. So our goal is really trying to build an open source community for AI for drug discovery. So basically, then I think there could be like two types of users. And the first type of user is really like scientists, especially people working on like machine learning, working on AI. So right now in the AI community, in the machine learning community, So there's also like a huge interest in working on drug discovery, but they may not have the right knowledge, right? They don't know like which task they can work on, what are the most like important tasks in this domain. So in TorchDrug, we basically like benchmark a bunch of different tasks, like the ones I just mentioned. We benchmark a bunch of different important tasks in this domain. And for each task, we provide some like public data sets and also the evaluation metrics. We try to minimize users' domain knowledge. So for people working in machine learning, they can mainly work on like designing new machine learning algorithms. Okay, so this is the first type of audience, mainly for people working on AI for machine learning. So they can focus on, if they want to work on drug discovery, they know what they can work on, right? They know the important problems and they can focus on developing like new algorithms. So this is the first type of audience. And for the second group of like audience is of course for people working drug discovery, right? Because now we have this like open source platform which basically already implemented the state-of-the-art machine learning algorithm for drug discovery. So if they have data and they can leverage the latest machine learning techniques for their problems. So this could be used for both like academic researchers working on AI for drug discovery and also industry practitioners. For example, many like right now we have many AI for drug discovery startups. Many of them may be able to leverage our efforts.
And then as far as the sort of challenges and complexities that are faced by people who are working in the sort of scientific aspects of this domain, biologists and chemists and people working for pharmaceutical companies, what are some of the challenges and complexities that they face in doing drug discovery in sort of the existing state of the art in the absence of AI and some of the new capabilities that this might unlock for them?
Somehow I already mentioned this like in the previous questions, like for people working on artificial intelligence or machine learning, right? The main challenge is like, wow, it's a very exciting field, but I don't know which problem I should work on, right? And then TorchDrug really basically provides like a set of like really the most important task in this domain. So they know what they can work on, right? The same case like for people like working like biologists or chemists, they have good knowledge about drug discovery, but they are not so familiar with like the latest advancement of like machine learning models. They don't know which model they should use for their specific task. And then TorchDrug really basically implements the state-of-the-art machine learning algorithms or models for their task. And also, I think another good thing about TorchDrug is like, because TorchDrug like it supports different tasks, and it basically also covers different type of data, as I mentioned in the beginning. So TorchDrug basically right now supports analyzing two type of data. One is like molecules, small molecules, which are mainly like by chemists. We are also like able to analyze biologic graph, basically mainly like the interactions between different biological entities, like for example, the interactions between drugs, proteins, disease. So these complicated interactions are mainly interested by biologists. And TorchDrug basically provides a solution to both analyze the small molecules, the molecular structure, as well as the biological network. So which are usually analyzed or processed separately by chemists and also biologists.
Also, in terms of the, I guess, collaboration opportunities that it opens up for the sort of chemists and the biologists in the research arena, wondering how some of these AI technologies are able to speed up the process and simplify some of the communication aspects of people who are working in these different fields and sort of the two different stages of the workflow of discovering these different drugs.
Really, like TorchDrug right now is able to support analyzing both type data, right? So it's able to, for example, like for understand molecule, we can either analyze it based on its chemical structure, which is mainly done by computational chemists, right? And also we can understand a molecule according to its interactions with other entities, for example, with proteins, with disease, right? So these many biologists care about, right? And TorchDrug allows to like simultaneously or support the analysis of both type data.
In terms of the actual implementation of the TorchDrug project, can you talk through some of the ways that it's designed and some of the sort of architecture and software development aspects of it?
So TorchDrug initially, like, as I said in the beginning, so we mainly support like the analysis of like small molecules and also biometric knowledge graph. So both type of data, they are graph data, but they are quite different. Small molecules, they are graph, but they are very small graph, right? Which usually has around like tens of like atoms or tens of nodes. But then biometric knowledge graph could be very huge. Basically, it involves like the relationship between different kinds of like drugs, proteins, and disease, which could have like millions of like the graph could have like millions of nodes, which is very huge. In the beginning, we tried to design a system which could process both type of graph. We basically trying to consider this. We are able to process small molecules, small graph, as well as like big graph. That's the key we try to consider when we first designed this system.
As you have been exploring the overall problem space and getting more sort of understanding of what's involved in some of the scientific aspects of drug discovery and some of the ways that it's being used by scientists and by the AI community, how has that helped to drive the particular focus of the TorchDrug project and some of the priorities as far as directions that you might want to explore with it?
So right now for TorchDrug, we mainly focus on small molecules. But now recently, drug discovery based on small molecules. But like recently, starting from last year and this year, there's a huge interest in the community, in AI or in biological communities. There's a huge interest in developing like big molecules, like for example, proteins, like peptides or antibody for drug discovery. Okay. So in the future, like we also plan to support like big molecule discovery, like protein design and protein reputation learning. So that's basically what we are doing now and what we plan to further support in the future through TorchDrug. Recent like breakthrough by DeepMind on protein structure prediction with AlphaFold 2, right? And that's really like brings a lot of like attention or interest in proteins, in protein understanding or protein reputation learning or protein design. And that's definitely something we want to support in the next release.
In terms of the sort of assumptions that you had going into this particular problem space of drug discovery, given your understanding of the sort of networked data sets and graph learning, what are some of the assumptions that you had that have been challenged, or some of the ideas that you had as far as the potential approach or potential capabilities that have had to be sort of adjusted or reconsidered as you've progressed further through the implementation and engagement with the community?
So by far, you see, like we usually represent all the molecules, either small molecules. So for small molecules, we usually represent them as graphs. And then for proteins, we usually represent proteins as sequence, basically a sequence of like an amino acid. Okay. But that's actually a sort of like, there's some limitation there because for molecules, either small molecules or protein, a more natural representation should be their 3D structures, right? Because molecules, naturally, they are represented 3D structures. So that's a big limitation for graph-based methods because graph-based methods only can capture the relationship between the atoms. They cannot capture the geometric features of those molecules, which are very important for drug design. For example, like if you want to design a small molecule, so ideally the shape of the small molecule should be complementary to the shape of the protein surface, right? So in order to model that, so it's important to leverage or to model their 3D structures instead of like only based on their 2D graph representation. So definitely, and actually there's also a trend in the community. So for molecule or protein modeling, so now we are going beyond 2D graph representation learning to 3D structure modeling.
In terms of the sort of graph characteristics of these molecular structures, I'm wondering what are some of the complexities that are inherent to the problem domain where, if you're doing some graph research, then maybe you're able to enforce that it is acyclic in nature, whereas with chemical structures and chemical compounds, you want to have certain cycles involved, and just being able to understand the molecular composition from a network perspective and just some of the interesting problems that brings into the sort of overall discovery and research space.
Right. So maybe I can mention a few important complexities or challenges. The first question is really to like the number of like label data. So usually, because if we want to build up a machine learning model, so then it's important to have enough training data. Like for example, in computer vision, in natural language processing, in speech recognition, we have many label data. But in drug discovery, so actually we don't have so many label data, right? That's in general a big challenge. That means like we want to develop models which is able to learn from very few label data. So of course, this is somehow like already like active study in the machine learning community, which is known as like a feature learning or meta learning. But this kind of techniques are particularly important in drug discovery because in this domain, the number of label data is really limited and it's very computational. It's very expensive and also time consuming to obtain the label data. So these are the first challenges for molecule modeling for drug discovery. The second challenge I think is really to when we're trying to model molecules, so we basically have to take the symmetry of the molecule into consideration. If we represent a molecule as a 3D structure, then a 3D molecule structure representation should be a rotation and a translation invariant. And so when you try to develop your model, that's something you have to take into consideration. If you rotate or translate your molecule, some of the properties, for example, the energy or the property of the molecule should remain invariant. Okay, so that's one type of symmetry we want to consider, which is invariancy. But there's also another property which is called covariancy. So for example, given a molecule, if we want to predict the forces over each atoms, then so in this case, the forces over the atoms should be rotation and the translation equivalent. What does that mean? So if we have 3D molecule structure, you rotate your molecule, then the forces over the atoms should be rotated accordingly. So this is called a rotation equivalent. So when you try to build a model, so that's something you need to take into consideration. So this is by far a very active research in molecule modeling.
Another interesting aspect of the TorchDrug project is the fact that you are trying to make it accessible and understandable to these two different communities of scientists and, chemists and biologists, and the AI community who are familiar with some of the sort of deep learning concepts. And I'm wondering what your approach has been as far as how to design the APIs of the project and the sort of documentation and tutorials to make it accessible to these different communities with these varying backgrounds?
That's a really good question. And I would like to thank my students for these efforts. In the beginning, we first identify a set of important tasks in drug discovery. And then for each task, we first provide APIs to some important public data sets. So the user don't need to deal with the data pre-processing. For example, for people working in machine learning, they may not have the experience to pre-process the molecules. We have an API to upload the data set to pre-process the data set. So the users do not need to take care of the data pre-processing stage. And then, of course, then we have some standard. We provide a bunch of different state-of-the-art algorithms which are trained on the public dataset. And at the same time, we also provide standard evaluation metrics. So once you are able to train your model, and then so we have some standard modules to evaluate the performance of your algorithms, right? So basically, we provide some open public datasets and also standard evaluation methods, so that even for people working in machine learning, they don't need to worry about the data pre-processing and also the evaluation. They just need to, for example, eventually all the data will be represented as graphs, so they can only focus on the machine learning side, basically how to develop machine learning algorithms or deep learning algorithms to analyze graph data.
In terms of the workflow of somebody who's using TorchDrug to be able to build a model or be able to do some of these search space optimization problems of the de novo molecule design or the sort of retrosynthesis capabilities, I'm wondering if you can just talk through just some of the overall workflow of getting started with TorchDrug, setting up the problem design, figuring out sort of what are the goal states that you're optimizing for, and then executing and iterating on the experiment.
So usually, let's say we have a protein target, okay, and then maybe through some wet lab experiments, so we can have some initial training data. We know some molecules, they are a potential binder. We basically positive molecules to the protein targets. We also have some negative molecules, right? So then in this case, we can basically try to predict the binding affinity for a molecule. Okay, so this is basically related to the task of molecule property prediction in TorchDrug. So we have a molecule, we want to predict its chemical properties, for example, either bind or not, right? So once you have a set of label data like this, the users can train a molecule property prediction model based on the training data. Okay. And once we have the molecule property prediction model or binding affinity prediction model, so that model can be used in the molecule design and optimization task, because in molecule design and optimization task, we need to have a reward function. basically trying to tell the algorithm, okay, whether this molecule is good or not. Because the novel molecule design and optimization, the essential idea is like the algorithm, we use reinforcement learning. So the algorithm is basically try and error, right? So you try this molecule and then the environment will tell you, okay, whether this molecule is good or not, right? Maybe the algorithm will further explore around that like area. If it's not good, maybe the algorithm will like go to move to explore other area. So then you can see like during this process, the essential part is like we need to provide a reward function basically to tell the algorithm whether this molecule is good or not. So good or not basically depends on like the type of like molecule property you want. So of course the most important one is usually the binding affinity, whether this molecule can be bind to the protein target or not, right? And that's why I said like before working on this molecule design and optimization or molecule search module, we have to train a machine learning predictor basically to predict whether a molecule has desired property or not, or maybe like whether the molecule can bind to the protein target or not. In order to do this, we usually have to have some initial training data. So we have some positive molecules which can be bind to the protein target, and also we can have some negative molecules which they are not able to bind to the protein targets. So this can be done through some like assays. We don't need to have many in the beginning, right? But we can have some in the first place. And then once we have the machine learning predictor, and then we can use that to search for better molecules using the molecule design and optimization module. By doing that, so we are able to search for maybe a set of like potentially better molecules. For example, we can search for like 1,000 molecules, which could potentially be a better binder. Okay. And then these 1,000 molecules, like we can maybe send them back to the wet lab experiments so we can test them again. And then by doing this, we can get a better training data. Those training data could feed back to our machine learning predictor, because now our machine learning predictor has more training data, right? And so we can refine our machine learning predictor, and then the new machine learning predictor we send back to the search module, and then we can find, based on the new machine learning predictor, maybe we can find better candidates. And these more candidates will be sent back to the wet lab. So basically by doing this, we can sort of like form a loop between the computational side and also the wet lab side. And this is basically how the whole workflow functions.
You mentioned the AlphaFold project, and I'm wondering, given the fact that you are trying to optimize for being able to bind to these various protein targets, what sort of potential impact do you see as the availability of these new sort of protein folding structures and the information that it provides to the biological community, how that might impact just the overall aspect of drug discovery and some of the ways that you might be able to integrate that information into the TorchDrug toolchain?
Yeah, so that's a very good question. Because usually for drug discovery, there are two types of approaches. One type approach is called like ligand-based approach, and another one called like structure-based design approaches. So for ligand-based approaches, usually we don't make use the structure of the protein target. So we mainly like use the ligand information. So like what I said, for some ligands, they are positive, for the others, they are negative. So we can just train a machine learning predictor only based on the molecule information, right? Of course, this is not ideal, because in this case, we don't leverage the 3D structure of the protein information, right? The target protein information. So then a better solution is really the structure-based like a drug design. So in this case, leverage the 3D structure of the protein target. So basically, we're trying to find a good match between the protein target, their 3D structure, and also the small molecule. Okay, with AlphaFold 2, because now we are able to basically obtain the 3D structure of almost all the human proteins very accurately. So I think it really basically makes all the structure-based drug design possible, because for any drug targets, now we know their 3D structure, and then we can mainly focus on developing technique like structure-based like drug design, right? Because previously, like for some targets, we don't know their 3D structures. There's a big challenge there. But now for all the targets, we know their 3D structure. And then we can just like focus on designing the small molecules or even proteins, which are able to bind to the 3D structure of the drug target.
In terms of the sort of technical aspects of the foundation that you've chosen for the TorchDrug project, I'm wondering, what was the decision process and some of the sort of aspects that you were looking for as you were deciding what to base the overall project on, and how that ultimately ended up leading you to use PyTorch versus TensorFlow or any of the other machine learning frameworks that are available?
Maybe I think that somehow it's also related to how the evolution of like community development between TensorFlow and the PyTorch. in the beginning, TensorFlow was very popular, basically dominating the whole community, right? But then after PyTorch released, I think the scientific community is quickly adopting PyTorch because it's easy to use. And I think with PyTorch, I think we are able to really prototype a research idea. And that's why in scientific community, PyTorch is really increasing of popularity. And actually the decision is not that difficult to make because in our group, basically all my students, the new networks based on PyTorch. That's actually not a really difficult decision to make. In the PyTorch framework, there are also already quite a few frameworks which are able to deal with graph because our techniques are mainly based on graph. There are already quite a few frameworks which are able to deal with graphs in PyTorch. For example, PyTorch Geometric, which PyTorch a library which are specifically designed for graphs. Okay, and also a DGL Deep Graph Library, okay, which are very popular in the graph machine learning community. Okay, but remember that those graph-based PyTorch library, so they are mainly designed for handling arbitrary graphs, not only a molecule graph. They mainly designed to support any kind of graph like social networks. They could deal with molecules as well. But for us, we really want to design a specific library for drug discovery, for handling for molecules, proteins, and maybe bimental knowledge graph. So also molecules, they can be represented as graph, but actually there are some specific operations which are very unique to molecules. So that's why in our framework, we actually design some specific operators which are used to deal with molecules, to deal with molecule graph. And now we are also extending that to deal with proteins, as well as 3D structures. Because I said in the beginning, now we are sort of trying to move from 2D graph to 3D structure, which is actually missing in many existing graph-based library. And now we are also trying to deal with different kinds of operations on 3D structures.
To the point of the sort of graph aspects of it, I'm wondering if the target of small molecules helps to cut down on some of the sort of computational cost and complexity because of the fact that the size of the networks are relatively small. And if there has been any, specific to the graph library aspect of it, if there have been any sort of unique capabilities in Network X that you're leaning on, or if you've also considered using or have experimented with some of the projects such as NetworkIt or GraphLib.
We mainly focus on developing deep learning algorithms for basically graph repetition learning, graph neural networks, or knowledge graph embedding techniques. And there are some, of course, some traditional graph-based or network-based analysis algorithms, but those are just mainly traditional network analysis software. For example, they want to calculate the page rank, clustering coefficient. But those are not the type of techniques we want to use for molecule modeling because we mainly want deep learning techniques based on techniques like graph neural network, graph repetition learning, or geometric deep learning. So these are new type of techniques that we want to develop for molecule modeling, which are quite different from traditional graph analysis or network analysis software. Yeah.
In terms of the just overall space of the sort of drug discovery research and some of the complexities that are there, I'm wondering what are some of the biggest open questions in that area and some of the ways that you're hoping to be able to apply the capabilities of TorchDrug to be able to simplify or speed up some of that research?
So in general, for drug discovery, the very fundamental question is to understand the interactions between, let's say, protein and ligand, right? And also interactions between protein and the protein, which is the key to drug design. So let's say you have a protein target, and then if you want to either design small molecule protein to bind to the protein target, then it's really important to understand the interactions between either the interactions between protein and ligand or the interactions between protein and protein. I think to understand the interactions between the two is really the key to drug design in the future. And also it's very challenging because compared to other problems, as what we discussed, now we have made huge progress in terms of a protein structure prediction based on the AlphaFold2 system, right? But it's still a very challenging question to model the interactions between proteins because the number of label data is just very limited in protein-protein interaction or in protein-ligand design. So for protein structure prediction, so we still have many label data or training data. And that's why actually one of the key reasons why AlphaFold2 is very successful because we have a lot of training data to train a model. But for protein-protein interaction or protein-ligand interaction, we don't have so many label data. So it's going to be a very challenging problem. Okay, so I think in the future, if we can make some significant progress on either of these two problems, I think really like we can make a huge advancement in drug design. So in the future, we will try to benchmark the two tasks. One is protein ligand interactions, mainly support for small molecule discovery, and also protein interaction, mainly support for protein design. So we want to benchmark the two tasks and also try to push forward the progress of the two fundamental and also really two key tasks in drug discovery.
And so in terms of your experience of building the TorchDrug project and exploring the overall space of drug discovery and sort of digging into the research, I'm wondering what are some of the most interesting or unexpected or challenging lessons that you've learned in the process?
I think the most challenging thing is really the problem itself is really multidisciplinary, right? You need to have like expertise from both like machine learning and also drug discovery. I think that's really, I feel like where the most challenging thing are. We also have a lot of collaborators in the biomedical side. I think really like communication is always like difficult in the beginning because we speak different languages, right? And we have a totally different mindset. So I think that's really like adds a lot of like a complexity there in terms of communication. But I think but with more and more communication, things getting better. So I think definitely that's in general the most challenging thing, especially for people working on AI, right? So because we don't know what are the most important problems in this domain, so we don't know where we can get the useful data set, right? So another thing is like for building a system like TorchDrug, it's basically the same problem, right? So for us, we are mainly like machine learning researchers focused on developing new algorithms. But then TorchDrug is a machine learning system, so it's not enough for people who only have algorithm development skills to build a good machine learning system. So I think unfortunately, like in my groups, we have a student who can understand both like a machine learning algorithm and also have a very strong system development capability, right? I think in general, like I feel like in this domain, always the most challenging thing is really like the problem is really multidisciplinary. So we need to have like expertise from machine learning, from chemistry, from physics, right? And even for machine learning, we also have like algorithm development and also system development, which are also quite different.
Yeah, it's definitely interesting, some of the sort of human problems that crop up when you're trying to put together two different groups of people who have different interests but have sort of a combined goal, and just some of the shared vocabulary that you have to figure out where, you know, each domain has their specific ways of discussing things, but they don't mesh well together until you're able to get them all talking together and establish a new sort of vocabulary.
Right, but I think in general it's important to have like a really open mindset and then basically appreciate the efforts done in other domains and also very open to learn from them. Yeah, it's important also to be quick learner because like for many things it's totally new for us. Like pretty much all the biologic like knowledge is totally new to us, so we have to learn from scratch. Then I think it's really important to be a quick learner as well.
Absolutely. And so for people who are interested in exploring the space of drug discovery or sort of actually working in that field, what are some of the cases where TorchDrug might be the wrong choice and they're better served with the sort of established experimental practices for drug discovery or, you know, using different computational approaches?
For drug discovery, because like of course right now machine learning is some trendy techniques, but before machine learning there are also some traditional approaches to drug discovery. For example, those like based on traditional physics-based methods. So for now, TorchDrug, we don't support those techniques, right? We mainly support like machine learning-based techniques for drug discovery. So in that case, I think it may not be the right tool if we want to explore more traditional physics-based approaches for drug discovery. Okay. At the meantime, like now in the community, we are also trying to using neural networks or using deep learning algorithms to approach those problems traditionally studied based on physics-based methods, as the one I just mentioned, like the interactions between protein ligand. So it used to mainly like based on traditional physics-based methods. Now there's a lot of interest in developing neural network-based approaches in deep learning algorithms for those kind of problems. And now we are also seeing like some exciting progress along that direction.
As you continue to work on the TorchDrug project and continue to explore the overall space of drug discovery and build out the community around the work that you're doing, what are some of the things that you have planned for the near to medium term and any particular areas of help or contribution that you're looking for?
So basically, as I said, right now, TorchDrug mainly support a small molecule discovery. Another really big space for therapeutic discovery is really protein antibody design. So which is something that we plan to support in the near future. So right now, we already have a module called protein representation learning or protein design in our platform, but it's under development. So we hope to release that module in the near future. And this is one thing. So another one is more related to the techniques. So right now, for small molecules, for proteins, small molecules are represented as graph, and for proteins are represented as sequence. So in the future, we really want to go beyond the current sequence or graph representation to 3D structure representation. So we can model molecules and proteins as 3D structures, and then we can start to model their geometric features, which is really important for drug design. So how to effectively combine the computation methods, mainly the machine learning algorithms, with wet lab experiments in a more effective way is really important, right? So in this case, there's huge interest in the community to use active learning algorithms. So basically, for the machine learning algorithms, so because in machine learning, there's some passive or active. So passive, basically, you just learn from what people give you. Active, basically, you learn from where you want to learn, right? That's actually really a good way to combine the computation methods, basically machine learning algorithms, with wet lab experiments. So based on the machine learning algorithms, we can suggest a set of drug candidates or bioassays we want to conduct. So by doing that, so we can sort of obtain the kind of training data we want, right? This is related to active learning, basically based on the current machine learning model where we want to acquire the knowledge. So we can suggest a set of molecule candidates, drug candidates, or bioassays to let the wet labs to validate those molecule candidates and to get the training data we want. So in this scenario, active learning is very important. It's a good way to really effectively combine the wet lab experiments and also the dry lab or computational methods.
Well, for anybody who wants to get in touch with you and follow along with the work that you're doing, I'll have you add your preferred contact information to the show notes. And so with that, I'll move us into the picks. This week, I'm going to choose the Rope project. It's a refactoring library for Python projects that has a lot of useful capabilities for being able to do sort of ad hoc restructurings of Python projects. The API is not as accessible as I would like sometimes, but for the cases where you're trying to, move a module to a different directory structure and make sure that all the imports are updated accordingly, it's one of the best ways that I've found to do that. So definitely worth taking a look for some of your more complicated refactorings. And so with that, I'll pass it to you, Jian. Do you have any picks this week?
I think in general, I hope the pandemic will be finished very soon, so we can really attend conference and see all the friends, the colleagues physically.
Absolutely. Yeah. Can definitely second that sentiment. So definitely appreciate the time you've taken today to join me and share the work that you've been doing on TorchDrug and the contributions you're making to the problem domain of drug discovery. It's definitely a very interesting project and an interesting problem domain. So I appreciate all the time and energy you're putting into that. And I hope you enjoy the rest of your day.
Thank you very much. You too.
Thank you for listening. Don't forget to check out our other show, the Data Engineering Podcast, at dataengineeringpodcast.com for the latest on modern data management. And visit the site at pythonpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts@podcastinit.com with your story. To help other people find the show, please leave a review on iTunes and tell your friends and coworkers.